What I will speak about today, this is about metadata standardization. But for a second, let's just go back and see what are we really speaking about. Indeed, what we have is these lots of numbers, these zeros and ones, and that's the data. That's actually just an information representation. And the question is, which comes afterwards, what is metadata? This is actually the contextual information to retrieve the information and connect it to knowledge. If you know that those zeros and ones, actually, they represented bits corresponding to ASCII tables, you can then convert to characters, and then you will immediately be able to read. Reading it might not be enough. You still have to know English, and you have to know all the terms. What are the, like, transformation, vectors, and so on and so on. If you have these knowledge bits, then with the help of the metadata, which explains the data, you can then get the information of your data and connect it to your knowledge. And with this, you can extend your knowledge. And why do you do all these things? Because then you have your data and metadata. Indeed, you can start using it because you can understand it. You can really use it as an input for use. There can be an application where you want to really apply this data and use this data for searching, for analysis, or for visualization. When you use this data, then as a result of your application, you will actually produce new data. There will be a new output, a new information. And it's not enough just to store this data, but it's also important to attach the new metadata to this. So then the new information is properly preserved. And that's actually what we would like to speak about, how to do that. As Heiko has mentioned, today we will concentrate on a very simple experiment, and we will try to do something very simple so that you can all have a feeling how you can then apply it in your lab. But first starts about an abstract. What is a data object? We have a data object, which we just measured, for example, as an experimental object, and we have to explain what it is. We have to provide all the context for its proper interpretation and for connecting it to knowledge. So if this data object is really actually something what I measured, like the data object XXX, indeed, I have to explain it properly. I will have a long story. I will have a long story which will describe what kind of experiment I did, which instrument I used, what were the instrument settings, what was the sample I used, how it was prepared, how was the raw data collected, how it was then corrected, calibrated, reduced, analyzed, and so on. And so it becomes a long story, which you can read. But how can we use it? What happens if you have another data object? You make another measurement. Even if it was a very similar experiment, what you've done, you would still have to write the long story again. For every measurement, for every data object, you will have a long story of what is it about. You really have all the context needed to provide it. And that's certainly not the way to go. It will be very difficult to work with such explanations attached to the data. So instead of having long stories, what needs to be done is to use a parameterized story. So indeed, for the data object to explain our XXX, we will use a new term, an experiment, which is a parameterized story of which kind of experiment I used, which kind of instrument I used, all the things what I just mentioned. But this is now organized in a way that these are parameterized, and I can attach data, metadata, which is explaining which experiment type I used, which instrument I used, and so on. And now if I do a new experiment, the only thing what will change is that I have a different observable data object y, that's what I'm measuring right now. And metadata is changing according, like the sample has been changed. But I still have the whole structure of my concepts and meta concepts, and I can use this concept afterwards when I want to interpret the data. Knowing this concept, I can already start writing my applications, even without I would have the data and the metadata objects. So let's go back to our experiment then, and let's have a look what we propose. We say that you have to collect your concept, but how? First, you always have to have your physics model. Anyway, that's how you start. But you really have to think about this physics model and say that I want to make an experiment data model, which is based on this physics model I have to express my experiment parameters from this physics model. I have to match the two together. And then I can really have measured numbers like the angle of the slope or the length or the mass of the car. These can all be then connected to physics concepts. Indeed, what needs to be done, that we have to organize our experiment parameters. And these experiment parameters are the physics concepts to describe what and when needs to be set or maintained during an experiment, what needs to be measured and calculated. This, if you arrive to that level, that's what we call, you've got a conceptual design model. It's very nice. You have already described your sample environment, your instrument, your data processing, your experiment in general. Everything is connected to physics. So then if you know physics then and the physics concepts, then you know what you are speaking about. You can really immediately interpret and use it. Indeed, what is important that in this case, we have an implementation independent physics model used, which means that indeed, we describe what has happened, but we don't describe how it has happened. It doesn't tell how exactly we performed the experiment. It tells what we wanted to measure, what we used to measure, what we did measure, but it doesn't tell how we did it. If you now go away from just data modeling your experiment as such, and you would like to go for reproducibility, if it's also important for you that someone else would like to repeat your experiment and repeat your experiment and do another findings, what is needed is that you have to do one step further. It's not enough just to have a conceptual design model. You have to concentrate and then start working on a technical design model. What is the main goal? Instead of just describing what was the pressure in a chamber, for example, you have to describe how this pressure has been produced and how it has been maintained. As soon as you start thinking about how you can do that, you will realize that what you do here, it will be implementation specific. It will really depend on what kind of instrumentation used, what were the possibilities with this instrument, what were the limitations of what you had to also cope with. It's not necessarily easy that someone else who tries to repeat the same conceptual model would use the same instruments. So you have to guide your peers how you have done your experiment. You really have to speak about the technical details, not only just the physics model. And in our experiments, as it has already been shown by Heiko, it's difficult. We've got lots of details of our instrumentations, very heterogeneous experiments we are doing, and very complex instrumentation we are using. Also the sample preparation, it's very difficult to follow. You can easily see screens like this when you are controlling your experiments, and behind each of these small boxes, there are thousands of further numbers and concepts. What is speed, what is base speed, acceleration, backlash distance. You have to explain all of these things, what you have applied during your experiment. You have to describe the different coordinate system, what you have used, and also the different algorithms, what you have applied while you've been doing, for example, backlash corrections or calibrations or anything like this. Otherwise, these are just numbers and you don't know what do they mean. The only way forward is to describe it somewhat properly. What do we mean properly? It's very important that you can be lost in this process. If you go down and describe everything, even the last screw, what you have to then put in place, it's difficult. It is really the role of the community to decide what should be the standard. How deep a standard technical design model should go for reproducibility, it must be defined by the community. Community, it is actually what is defining what we need to be able to understand what you are speaking about. So we are doing the data modeling for a community, together with the community. That means that we have to have controlled vocabulary of concepts where we do understand what do we mean by these concepts, these experiment parameters. We have to have clear relationships between these concepts and the meta concepts, what we are describing, which is building up this parameterized story. Very important thing is also the cardinality and optionality. We have to highlight if in a certain experiment something really brings a vital information. You cannot just forget about this. We do need to know what was this parameter, what was this and that. If something is good, maybe you can, but not necessary, then you may want to label it as optional. We all know, we all should know what you are speaking about. The concept is introduced, but maybe the use of this concept when you describe your experiment might not be necessary. So you can also provide optional parameters and not just required parameters. You certainly should use some standardized unit. At least your community should agree on which kind of units you would like to use, and it should be understandable by everyone. I highlight again, I have already said it several times, but I highlight it again. The most important thing is a community agreement. When we have a community agreement and we also agree on the data format or an API, how you can reach the data, then we can start writing tools for the community, so that the community will have common tools and applications which can work with the data even before the data has even collected. For these purposes, Heiko mentioned, we use NeXus. NeXus provides a possibility for such a hierarchical data modeling, what we really need when we are organizing our concepts and meta-concepts. It brings the possibility to easily define these concepts. It brings tools, which is then expressing all these definitions of the concepts in a controlled vocabulary, actually in a glossary, in the NeXus glossary. Also, there is tools which are automatically converting it to an OWL file, so it's providing a NeXus ontology of all these concepts. There is an HTML page automatically generated, so also the researchers can easily go and read all these concepts. It's extendable. As it has been highlighted, originally it was for neutron, X-ray, and muon sciences. Here in FAIRmat, we do much, much more. But since it's extendable, there is a NeXus definition language, NXDL, which helps us actually to describe all what we would like to have, all the definitions and the relationships within the definitions. That means that we can just add all what we want, everything new what is needed in our experiments. And the NIAC, the NeXus International Advisory Committee, provides us with a standardization body and the standardization process, how we can really make our individual thoughts into a standard which is then communicated and can be used in the community. Practically, we also have tools for data visualization, verification, and validation. So when you have a data object, we can really validate if it corresponds to the standard, if what is needed by a concept, that's what actually provided by the data. We can't really check and validate deeply, but at least we can verify that the data structure is the same. The shape of the data object is what is expected in such a scenario, in such an experiment. How it works in NeXus, indeed, we've got these base classes as building blocks, and we've got the application definitions. Those has been highlighted by Heiko already. I would like only just to highlight that all the points, what we need. You remember, we wanted to describe instruments, sample, the data analysis processes, the users, also the notes during an experiment. That's all provided by these base classes, NX instrument, NX sample, and so on. And we've got lots of more. Indeed, we have 57 base classes available, 57 concepts which you can use, and 34 application definitions. That's already quite some. But I would like to also highlight that since FAIRmat also joined the NeXus community, in 1 year, we added a lot more. So now if you check what's available in the contributed definitions, which is just recently added, you can see we've got 112 new base classes. we've got 20 more application definitions. It's very good that we can freely come up with our own concepts and propose it for the NeXus community for standardization. That's what you can see here. I'm showing one of the latest ones which we came up with, and the reason why I picked up this one, because this is actually which will be used in our hands-on experiment today. This is a very generic thing, NX sensor scan. When you would like just to make a scanning experiment, so you basically alter the sample environment, and then at each point while you are scanning, you do make measurements. How to describe it? What we can do is that we can have an entry, which is a description. Let me show it for you. We have an entry, which is an experiment itself. Here within, we can speak about the user. We can describe the sample. We can describe the instrument. And within the instrumentation, we have the environment, where we have the independent controllers, which are independently changing the environment settings, for example, temperature or pressure. Measurement sensors. Both of them are actually sensors where you can collect the values, but also timestamps for the values. You can know when your sensor was calibrated. And also there is a view how the sensor data can be also visualized. You can have a PID also attached to your regulation process, and you can also have data processing immediately attached to your measurements. All these things is covered by a sensor scan. So then whenever you just want to make an experiment where you are going from different environment settings and you do make the same measurements all around, you can immediately take advantage and start using this. If you need more details, indeed, that's what we also propose in our HTML pages, where you can read more. So all of these things which I just drafted quickly on the left-hand side, you can go deeper and you can read also the detailed information about all these fields and experiment parameters. It's not just that you can read them. You can also log in and immediately leave your comments. You can give suggestions. This is actually the community engagement process that we are also expecting the community to answer back. We do like this, or maybe the definition of the process, define the program that was used to generate the rules, the results file with the measured data and metadata. Maybe that's not clear enough to someone. You can propose a new formulation of the definitions also here, or a new structure. This we can all consider. We receive this, we can consider it in the next version. We can already put this in. So what is the situation? You've got all your data. And if you have a standardized application definition, then you can already collect the data and organize it according. But what happens if you collect data which doesn't fit to the standard? We propose that you should write your schema system. You should write your own schema. Maybe it's not standard yet, but you can already write it down. You can already define, what do you mean by this structure? Where do you get this information? What does it really mean? Not just write the numbers. Please also write the schema, write this new concept. You can also describe in human words, what does that mean? Because this is important. The left-hand side, that's fair data. The right-hand side, what we call fair ready data. Why is it just fair ready? Because yes, it's findable and accessible, but the concepts which you came up with, these are using your own vocabularies. They do not necessarily follow the FAIR principles themselves. They are not community standard yet. So this is not fair, but this is already fair yet ready, because if you have all this information properly stored, then you can already convert things to standard if it exists. Or if then a new standard comes up, then you can make all this conversion. You may want to assemble different concepts together or disassemble concepts. And with this, you can normalize your fair ready data and convert it to fair data at later point. Converting, assembling, and disassembling. That's what you have to do. And actually, we have already provided standards and proposed standards for ellipsometry, electron microscopy, atom probe microscopy. All these proposed standards are available under the web page, what you can see. With the help of this, we are providing a playground for you where you have already the necessary standards and standard data models, so you can really take your raw data, your ELN entries, and your data analysis, put them all together as data and metadata into a standardized data model, which can be then used in NOMAD afterwards for search, for visualization, and for analysis.